This is a short problem session where we will address some problems on the Cauchy-Riemann equations and its implications. Recall that we had defined the Wertinger derivatives in the following manner. So, recall that given omega contained in C, a domain, and F, a map from omega to C, which is differentiable when I say differentiable, it means that the total derivative exists. The function is real differentiable. Total derivative exists. Then the Wertinger derivatives were defined in the following manner. The z derivative dou f by dou z at a point z naught is defined to be equal to half of the partial derivative dou f by dou x at the point z naught plus 1 by I times dou f by dou y at the point z naught, and the z bar derivative dou f by dou z bar at the point z naught is defined as half of dou f by dou x at the point z naught minus 1 by I times dou f by dou y at the point z naught. And there was an exercise given to you which asked you to establish that the Cauchy-Riemann equation is equivalent to demanding that dou f by dou z bar is equal to 0. In this problem session, we begin by looking back at holomorphic polynomials, or what polynomials are holomorphic. Let f be a polynomial in z and z bar given by the following formula. Let f be given by f of z is equal to summation c n m. There are two subscripts where the n is for the exponent of z and m is the exponent of z bar. So, n comma m greater than or equal to 0, n plus m is less than or equal to d. So, this is how we capture a general polynomial. Notice that every polynomial in x, y in R2 can be written in this manner, and the problem is to show, or first it is to compute what is the Wertinger derivatives of such a polynomial. So, let me write down the statement, then prove that dou f by dou z is equal to summation c n m into n into z to the power n minus 1 z bar to the power m, where n comma m both are greater than or equal to 0 and n plus m is less than or equal to d. And how is the Wertinger derivative? So, this is at the point z. And how is the derivative dou f by dou z bar defined? Dou f by dou z bar at any point z is going to be, this is what we have to prove, n m greater than or equal to 0, n plus m less than or equal to d, c n m z to the power n, m z bar to the power m minus 1. Okay, let us try to prove this statement. So, before we go ahead with proving this statement, let us see that the laws of calculus also go through for both these operators, dou by dou z, both these derivatives, Wertinger derivatives, dou by dou z and dou by dou z bar. So, in particular, the first claim is to check that dou by dou z. I will not prove it for dou by dou z bar. The proof is going to be very similar. By keeping track of the right signs, you can give similar proof. What is going to be dou by dou z of f plus g? By definition, this is equal to half dou by dou x of f plus g plus 1 by I times dou by dou y of f plus g. But we know that the partial derivatives dou by dou x and dou by dou y, they are both linear as operators. So basically dou by dou x of f plus g is dou f by dou x plus dou g by dou x. So I'll just directly write it as half of, this is equal to half of dou f by dou x plus 1 by I times dou f by dou y plus half of dou g by dou x plus 1 by I times dou g by dou y. And this is equal to dou f by dou z plus dou g by dou z. So yes, the linearity is satisfied by the Oettinger derivatives. A similar proof will say that this similar statement can be made about dou by dou z bar. Another important property which the Oettinger derivative satisfies is the product rule. So basically, if you have dou by dou z of f times g, this is going to be equal to, let's see what this will be. This is going to be half of dou by dou x of f times g plus 1 by I times dou by dou y of f times g. So the product rule or the Leibniz rule for the partial derivative operator, that's already known, and that will give us, this is equal to half of, I'll just directly write down what it is going to be. This is going to be f times, or maybe let me not skip steps. This is going to be f dou g by dou x plus g dou f by dou x plus 1 by I times f dou g by dou y plus g dou f by dou y. And accumulating the correct terms, this is going to be f times half dou g by dou x plus 1 by I times dou g by dou y plus g into half dou f by dou x plus 1 by I times dou f by dou y. And that's going to be equal to f times dou f by dou z plus g times dou f times dou g by dou z plus g times dou f by dou z. A similar proof can be given for the operator z bar as well. Okay, now let's get to the problem. The problem, let me remind you what the problem was. The problem was to prove that the polynomial in z and z bar given by summation c n m z to the power n, z bar to the power n, when we compute the Oettinger derivative with respect to z, we get the first expression, and this second expression of is for the Oettinger derivative with respect to z bar. So I'll just prove this part. The other part is analogous, and I'll leave it to you to write it down. Let's just compute the Oettinger derivative of dou f by dou z. Okay, so f of z, so let f of z be equal to summation c n m z to the power n z bar to the power n. All right, so if we look at the Oettinger derivative dou by dou z of f at the point z, by what we have just established, this is just going to be equal to summation c n m dou by dou z of z to the power n times z bar to the power n. And I'm not writing down the, maybe I should write down once. The indices are going to be the same. What is of interest is what is inside. So let's see what happens here. This is going to be summation c n m z bar to the power m. Now by applying the product rule or the Leibniz rule, this is going to be dou zn by dou z plus z to the power n dou z bar m by dou z bar dou z. This is precisely what we will be getting by looking at the derivative of z to the power n, z bar to the power n. So recall that the operator dou by dou z is the same operator as earlier, the operator d by dz that we were talking about. So dou z to the power n by dou z is equal to n times z to the power n minus 1. Let's now look at what is dou by dou z of z bar to the power m. This is what we are interested in. The other one we already know. To compute this, what we will do is we will just compute it for m is equal to 1. For m is equal to 1, this is going to be dou z bar by dou z. And one should actually, I'll just leave this as an exercise to you. It's a very straightforward check to see that this is going to be equal to 0, because you look at the definition here. This is going to be equal to half of dou z bar by dou x plus 1 by I times dou z bar by dou y. And the function dou z bar by dou x is, z is basically x plus x minus iy, and dou z bar by dou x is going to be equal to 1. And what is going to be x minus iy, the y derivative of x minus iy, that's just going to be minus I. So this is going to be 1 plus 1 by I times minus I, which is 1 minus 1, which is equal to 0. So this is quite straightforward. And now by applying product rule, we have dou z bar to the power m by dou z is equal to 0. And therefore, if you come back to this expression above, this expression of dou f by dou z at the point z, this term vanishes, and hence dou f by dou z is going to be equal to summation n comma m greater than or equal to 0, n plus m less than or equal to d as the indices, c and m, n z to the power n minus 1, z bar to the power m. The corresponding equation for dou f by dou z bar is proved very similarly. The only observation in that case is that dou z by dou z bar in that case is going to be equal to 0. So in order to prove the second expression in this problem, you just have to focus on the fact that dou z by dou z bar, this is equal to 0, because we are looking at the second Wertinger derivative, one with respect to z bar, and the fact that dou z bar, okay, so I'll just leave this as an exercise and check that dou z bar to the power m by dou z bar, this is equal to m times z bar to the power m minus 1. The proof is exactly as in the case when we deal with the Wertinger derivative, the derivative of z to the power n. So before we do the next problem, let's also look at the Laplacian operator in terms of the Wertinger derivatives. So recall again that the Laplacian operator was given by dou square by dou x square plus dou square by dou y square. Let's use the definition of the Wertinger derivatives and write the derivatives in terms of dou by dou z and dou by dou z bar. Let's see how this goes. This is going to be equal to, what is going to be, so recall that dou f by dou z is equal to half of dou f by dou x plus I 1 by I times dou f by dou y, and dou f by dou z bar was half of dou by dou x minus 1 by I times dou by dou y, dou by dou z bar. So dou by dou x in particular, let's see, dou by dou x, this is going to be equal to dou by dou z. So dou for any function f, that's what I mean, it's given by delta. This is equal to dou f by dou z plus dou f by dou z bar. Check that this is exactly what the Wertinger derivatives will give. This is half of dou f by dou x plus 1 by I times dou f by dou y, this is half of dou f by dou x minus 1 by I times dou f by dou y. And what will be dou f by dou y? This is going to be equal to dou f by dou z minus dou f by dou y, and we have to be careful because this is going to be I times dou f by dou y. Okay, so let's now look at what is going to be dou square f by dou x square. That is just going to be equal to dou by dou x of whatever was there, and dou by dou x of this is going to be equal to dou by dou z of dou f by dou z plus dou f by dou z bar plus dou by dou z bar of dou f by dou z plus dou f by dou z bar. So this is going to be equal to dou square f by dou z square plus dou square f by dou z bar square, and by using the Clairaut's theorem, this is going to be equal to dou square f by dou z bar. Okay, let's now compute dou square f by dou y square in terms of the Oettinger derivatives. What will be dou square f by dou y square? We already have written down an expression for that. It's going to be 1 by I times dou by dou z of 1 by I times dou f by dou z minus dou f by dou z bar. And then there is a dou by dou z bar of 1 by I times dou f by dou z minus dou f by dou z bar. Okay, let's see what happens here. The i's will give us a minus 1 times dou square f by dou z square, and yeah, I missed a bar here. There should be a bar here, and there's going to be a minus of dou square f, or rather by dou z bar. There will be two of these by Clairaut's theorem, and then there is a dou square f by dou z bar square. Therefore, hence the Laplacian of f is given by dou square f by dou x square plus dou square f by dou y square, which will now become 4 times dou square f by dou z bar. So this is the Laplacian in terms of our Oettinger derivatives. Let us now try to get hold of a necessary and sufficient condition when we can say that a given polynomial is harmonic or not. So recall that while doing the previous problem, oh yes, maybe I should mention that at this point. This problem tells us exactly when our polynomial is going to be holomorphic. Notice that if there is any term with m greater than z to the c and m not equal to 0 for m greater than 0, then the derivative of f with respect to z bar will not be 0, and hence the Cauchy-Riemann equations will not be satisfied. So the holomorphic polynomials are precisely those polynomials where c and m, the coefficient c and m is 0 whenever m is greater than 0. So just like how we can give a characterization of what holomorphic polynomials will look like, we will also be able to talk about how harmonic polynomials will look like. So let me just write down the problem for you. Again, let f be the polynomial f of z equal to summation c n m z to the power n z bar to the power n. So notice that both z and z bar feature in here. The polynomial f is harmonic on C if and only if C and M is equal to 0 whenever both N, M are positive. The necessary and sufficient condition is that at least one of n and m should be 0. There cannot be polynomials of the type z to the power 2, z bar to the power 3. There will be either a polynomial, either a monomial with z to the power n featuring in it, or z bar to the power m featuring in it. All other terms should necessarily be equal to 0. Well, we have already done the hard work to prove this. So the proof is now going to be quite straightforward. We are interested in the Laplacian of f. What will be the Laplacian of f? Laplacian of f is going to be equal to, let me just leave it to you to check that. This is going to be C and M times the Laplacian of z to the power m, z bar to the power m. Let's look at the Laplacian of each of the monomials separately. The first question is, what is going to be Laplacian of z to the power n? Remember that Laplacian can now be written as 4 times dou square by dou z bar of z to the power n in this case, which is equal to 4 times dou by dou z of dou z to the power n by dou z bar. And we have already seen that the Oettinger derivative of z to the power n with respect to z bar is 0. So this is going to be equal to dou by dou z of 0, which is 0, 4 times dou by dou z of 0, which is 0. So the Laplacian of z to the power n is 0. So in particular, the function z to the power n is harmonic. That's what we have just established. Let's also now look at what is going to be the conjugate harmonic, the conjugate powers, z bar to the power m. This is also going to be the same as the second derivative dou square by dou z bar dou z. Let me write it this way now. By Clairaut's theorem, we can do that. And this is going to be 4 by dou z bar of dou z bar to the power m by dou z. And we have just seen in the previous problem that this vanishes, just like how this vanishes. And this is equal to 0. So z bar to the power m, they also are harmonic. They all the Laplacian of such functions also vanish. So in particular, if you get back to the expression here, whenever either m is equal to 0 or n is equal to 0, the Laplacian always vanishes. Okay, let's now look at what is going to be the Laplacian when there are powers of both z to the power n and z bar to the power m. This is the expression which could create a problem. Let's see. This is going to be 4 times dou by dou z by dou z bar of z to the power n, z bar to the power m, which we have already seen is going to be 4 times dou by dou z of m minus 1 times z to the power n, z bar to the power m. And now applying the z derivative to the entire thing, this is going to be equal to 4 times n minus 1 into m minus 1 into z to the power n minus 1, z bar to the power m minus 1. So effectively, we have written the Laplacian of f to be equal to summation c n m 4 times n minus 1 into m minus 1 z to the power n minus 1, z bar to the power m minus 1, where both m comma n are now greater than 0. Both are greater than 0. Whenever okay, I should have been a little careful when I wrote indices earlier. I hope I have written greater than or equal to 0 earlier. Yes, I have written a greater than or equal to 0 here. We do allow in those cases n and m to be 0. But in this case, if n is 0 or if m is 0, what happens is that the Laplacian is going to kill the function. What remains is hence both n comma m greater than 0, n plus m less than or equal to d. And this is precisely what the Laplacian of f is going to be. But this is a basis of the collection of all polynomials of degree less than or equal to d, and therefore C and M is forced to be 0 whenever such an expression is demanded to be 0. The Laplacian of f is equal to 0 if and only if C and M is equal to 0 for all n comma m greater than 0. Either n is greater than 0 or m is greater than 0, this is equal to 0. So this is one stroke. We have the if and only if part, and with that we complete the proof. Let me conclude this problem session by solving one more problem. We will try to see when an entire function can be real valued. Entire already captures the fact that the function is holomorphic on the entire complex plane. So let f from C to C be an entire function. Then f is real valued. That means it takes only values on the real line only if f is constant. So the only possible real valued functions are constants. Let's give a proof of this. The proof is embedded in the Cauchy-Riemann equations. Let's use the fundamental theorem of calculus, like we had done earlier, to write the real part. So the imaginary part of f is already known to be 0. So let f be equal to u plus iv. F is real valued implies that v is equal to 0. We already now know that v is equal to 0. And what is going to be u? By the fundamental theorem of calculus, u of x plus iy is going to be equal to u of 0 plus integral from 0 to x u of t dt, that will give u of x minus u of 0, plus 0 to dou u by dou x of t dt. The fundamental theorem of calculus captures it this way. And now next is the y derivative. So the x is already there, it will be x plus it dt. So this is from 0 to y. So this is precisely the expression of u by using the fundamental theorem of calculus. Remember that f is an entire function. Now let us invoke the Cauchy-Riemann equation like we have done earlier, and this is going to be equal to u of 0. Dou u by dou x is dou v by dou y of t dt, and this is 0 to x, and this is 0 to y of, this now will be minus of dou v by dou x of x plus it dt. But what do we know about v? We know that v is 0 because f is a real valued function. Because v is 0, its partial derivatives are also 0, both are 0. And that means that u of x plus iv or u of z is equal to u of 0, which is a constant. That's precisely what we had come to prove, because f is equal to u in this case and u is a constant function.